Today we will integrate this expression 1 over 1 minus cos x with respect to x, and because cos x is in the denominator and we are subtracting it from 1, we need to make sure that cos x is not 1, otherwise this whole expression will become undefined, because division by 0 is not defined in mathematics. So I have taken this integral. I have let that x is between pi by 2 and 3 pi by 2, because in this integral cos is not 1 at any point. So now we are going to integrate this expression. So for that, the problem in this expression is that it has two terms in the denominator, and when there are two terms in the denominator, we are not able to basically use the linearity property of integral. We can't write that, uh, like we can't write it in the form of sum or subtraction of or difference of two terms, and we can't distribute the integral. So we need to make these two terms, we need to convert these two terms in the form of one term, and for that we need to rationalize this denominator. Whenever we have two terms, it doesn't matter whether we have minus or plus sign here, um, we can rationalize it. And when we rationalize this kind of expression, uh, we the integral becomes easier. So rationalizing, what does rationalizing mean? It means that we multiply the fraction with an expression which is basically conjugate of this expression, meaning that uh, we will multiply this expression by 1 plus cos x. We just change the sign of the second term, and if it was plus, we multiply or and divide by minus, and if in this case it is minus, so we will multiply and divide by 1 plus cos x. So I have multiplied 1 over 1 minus cos x by 1 plus cos x and divided it by 1 plus cos x too. This basically has no effect on the health of integral, cos 1 plus cos x, or 1 over 1 plus cos x is just 1. So 1 multiplied by this expression is again the same expression. So this one will be multiplied this with this 1 plus cos x, and in the denominator we have 1 minus cos x and 1 plus cos x, so both of these denominators will also be multiplied, and we can see that this is the form of a minus b into a plus b, and a minus b into a plus b, when they are multiplied, they give us a square minus b square. So in the denominator it will be 1 squared minus cos x squared. So 1 squared is just 1, minus cos x squared is cos square x, and 1 plus cos x is being multiplied with 1, so this will be 1 plus cos x simply. So 1 plus cos x over 1 minus cos square x, and 1 minus cos square x, we know that there exists an identity which states that cos square x plus sine square x is equal to 1. So from that identity, 1 minus cos square x is basically sine square x, and this becomes 1 plus cos x over sine squared of x. And now we see that the denominator doesn't have two terms, it simply has one term, sine square x, and this is much easier to calculate, because we can use this plus sign to our advantage and this one term in the denominator to our advantage, and we can just say that this is equal to 1 over sine square x plus cos x over sine square x. We can break this numerator because it has two terms, and we can write that 1 over sine square x plus cos x over sine square x. So we can write this in the form of this. And because if we take the LCM of these two terms, we will get the same thing, 1 plus cos x over sine square x. So 1 over sine square x is basically the reciprocal of sine is basically cosecant. So 1 over sine squared is cosecant squared, plus cos x over sine square x. We can write it in the form of cos x over sine x into 1 over sine x. And basically we are writing this so we can write it in the form of which can be easily integrated. So sine over cos is tan, so cos over sine will be cot, because cos over sine is just the reciprocal of tan. So this will be cot x, and 1 over sine x will be cosecant x. And we can see that now we have expressions which we can easily integrate. Cosecant square x and cot x cosecant x, both of these terms can be integrated. So we'll use the linearity property of integration and take the integral of these two terms separately. So integrating cosecant square x with respect to x, and integrating cot x cosecant x with respect to x. So we had the integral of cosecant square x. So basically the derivative of cot x is minus cosecant square x, and we had cosecant square x, not minus cosecant square x. So in order to compensate for the absence of that negative sign, we use the negative sign for with cot x, because whenever we take the derivative of this thing, it will be simply minus times the derivative of cot x, which is minus cosecant square x. So it gives us the positive cosecant square x, and that is exactly what we had here. So this will be minus cot x, because this term has the derivative equal to cosecant square x, plus we had plus cosecant x cot x, which is the derivative of minus cosecant x by same logic, and this will become minus cot x minus cosecant x plus the constant of integration. So this is our final answer for this question.